So first of all, welcome everyone to this parallel breakout session. And today we have Wojciech Samek, who will be conducting this tutorial. He is the head of machine learning group at Fraunhofer Heinrich Hertz Institute, Berlin, Germany. He studied computer science at Humboldt University, Zoo, Berlin from 2004 to 2010. Also, he was a visiting researcher at NASA Ames Research Center and received his PhD in machine learning around 2014. He has co-authored more than 100 journal and conference papers, predominantly in the areas of deep learning, interpretable machine learning, neural network, compression, and federal learning. Today he is giving a tutorial on explainable AI. So enjoy this tutorial. And I request everybody to put any questions if you have in the chat box or raise your hand. There is a raise hand option in a Zoom meeting at the bottom. So you can use that. So let's try to make this more interactive and more productive. Thank you. Please, Wojciech, you can go ahead.
Yeah, thank you very much for this nice introduction. Yeah, so today I will talk about my research on explainable AI. So I will start with a bit of basics, we'll present some of the techniques which are available, and also we'll discuss some applications and things which are currently being researched on. So since the beginning of machine learning, people regarded neural networks or machine learning models in general as black boxes. So there is this famous work on the perceptron from Frank Rosenblatt, and he already referred to the perceptron as a black box, getting some input and doing something and getting some output or giving some output. And these things, I mean, today our models are even more complex. We have deep neural networks with millions of or hundreds of millions of parameters, and they process complex data, images, time series data. And therefore no wonder like people for a long time regarded these kind of models as black boxes. So for usually people kind of feed data to these models, train them for some tasks, for example, to predict cancer from some images in dermatology, and then you get your model gives you some prediction, and the question which remains is, would you trust such a black box? So is minimizing the error which you do in your training phase a guarantee for the model to work well in practice? So does it really do something meaningful? And if you can't understand what the model is doing, so you cannot really verify them. Therefore, there is a huge need for methods giving you additional insights, explaining what the models are doing, how they solve the problems, and so on. So there are many reasons why you may want to interpret your models and your predictions. So the first reason I already alluded to, it's for trust reasons. So if you want to, if you have, especially in medicine and some applications which are very where like misclassification not an option, you may want to have a second check on your prediction. You may want to verify that the model really does the right thing. But also, like, there are some legal aspects, especially in Europe. People are talking about the rights to explanation. So if a machine learning model is doing a prediction which affects, for example, humans, you as a human may want to know why the model arrived at its decisions. But also, like, even if you don't care about that, and even if you're just an engineer and want to train better models, it's certainly an additional source of information. The better you understand your model, the better you understand its weaknesses, the better you can improve it. You can get rid of certain biases in the data and so on. So even for engineers, there is a good reason to have a deeper understanding of your models and the predictions. Finally, for scientists, if you're a scientist, a physicist, astronomist, neuroscientist, you may, so the important questions may be the why question. So you often you do not train your models just to predict, but you want to learn something about the nature, about the data, about the relations in the data, about relations between genes, about relations between different atoms or between different chemical compounds and so on. And so the hope is that our neural networks, our complex models can pick up these hidden relations. And once you can explain your models, you can better understand what's happening in your data. You can get maybe some new hypotheses about the data generating process and about the things you are interested in. So from that perspective, there are many good reasons to work on explainable AI, on explanation methods. And what I mean by explanation, you can see here in this picture. So today, if I talk about explainable AI, about explanation, I always refer to explaining an individual prediction. In this case, you have an image of a pool table, and your model predicts this image as pool table, and the explanation indicates which parts in the image were responsible for this prediction. So in this case, you see that the shape of the pool table and the pool balls are quite important for the model to predict this image as pool table, whereas the background is not so important. So this is like the things which we will look in today. I refer to these images as heat maps or attribution maps. So they attribute relevance to every input dimension, to every pixel. And there are many different techniques proposed in the literature to compute these attribution maps. One very simple idea is to perturb your input or to occlude your input. So for example, if you know that a network classified this input as castle, you may want to occlude different parts of the input, different parts of the image, and then see how the model reacts to this occluded image. Sorry. And you see that if you occlude the lower left part, the model predicts this image still as a castle. But if you occlude the area where the castle is, the model will not predict this image as a castle anymore. So from these occlusions, you may derive that this part in the image was especially important for the class castle. However, as you see, like this manual perturbation process is very slow. You need to occlude things all over the place with different size of a window, and you also assume some locality, because it may be that it's not that the evidence for one class is not localized in one place, but is maybe distributed all over the image or is distributed at several places. So then you would need to occlude using more than one window, which would be computationally infeasible. And also, like the perturbation you do may also introduce some artifact, because if you, for example, would occlude the image with a gray box, then the lower image could have been also classified as a castle, because a gray box on a hill looks like a castle. Therefore, this perturbation-based approach is also very easy, very simple, are not really recommended and have these disadvantages. Another class of methods, I refer to function-based explanation methods. So the idea is that you compute some, you regard your model as a function, your neural network as a function, and compute some simple quantities from it. For example, you compute the gradient. And many methods, many explanation methods proposed in the literature use gradients. You can very easily compute the gradient of your function. Therefore, it's like very efficient compared to perturbation-based. It's much more efficient. But also, like, especially when it comes to deep neural networks, gradient-based explanation methods has been shown to have certain disadvantages. One thing is that the deeper your model gets, the deeper your network gets, the more shattered the gradients become. So you have extremely variations in the gradients, and the information which you get becomes very noisy and unreliable. And also, like, in some sense, the gradient only captures some local effects. So it tells you that what makes a dog more doggish, but it doesn't tell you what makes a dog a dog. So it's like a local sensitivity which you compute, and not the explanation in this strict sense. Another category are surrogate-based explanation methods. Here, the idea is that if you cannot compute the explanation for the complex model, so what you do is you locally fit a simple model to your prediction. So you have a prediction and you locally fit, for example, a linear model around your prediction, and then you explain the linear model. So you explain the surrogate. So you're not explaining the model which you want to explain, but you fit a surrogate and then explain the surrogate. Of course, this is also like a nice idea, but it also it's more computationally more demanding, because you need to fit, you need to sample, and it also, like, the explanation may be kind of biased and unreliable depending how well you fit the model which you want to fit. And the better you want to fit it, the more sampling you need. So it's also like a method which is computationally in some sense demanding. The fourth class of methods I refer to as structure-based methods or propagation-based approaches. This is the most prominent method is LRP, layer-wise relevance propagation, a popular technique which was developed in Berlin and in my lab, and also with collaboration with some colleagues. And it's one of the methods for this category. And the idea is that maybe I will first give you like a high-level introduction and then tell you a bit more about the idea about it. So the idea was initially had is to decompose the prediction. So we thought, okay, we have a model which predicts for this image that it's a rooster, for example. And what we wanted to have is a decomposition in terms of relevance value. So we wanted to assign to every pixel a value Ri, representing how much this pixel has contributed to the prediction, so that in the end, the sum of all these relevance values make up or coincide with our prediction value. So it's a very generic idea, very generic approach. But the key question is like how to get this relevance values, those RIs. And the key idea of LRP is to use the model structure to get these values by propagating them back. So in some sense, you have your prediction in the first place. Your neural network gets this image and predicts that this is a rooster. On the way, some of the neurons get activated because they encode some shapes which are in the image or which are related to the rooster. Others are not activated, maybe they encode something else. And in the end, you want to redistribute. You want to redistribute the total evidence for the rooster, so the prediction value, backwards. But you're not doing it in one shot. You're not doing it as we saw in the other approaches, but you are doing it layer by layer. So the question which you first need to kind of answer is, how much evidence should be redistributed from the last layer to the second last layer? And then how much evidence should be redistributed from the second last layer to the layer below, and so on. So you kind of simplify the redistribution problem by doing the redistribution layer by layer. So you're not doing it in one shot. In one shot, it's too complicated. So you are kind of simplifying the problem. And this is a whole trick. And it especially works well in neural networks, because neural networks are compositions of simple functions. So at each layer, the function which you compute is very simple. It's just a Ray loop. So you know kind of how to explain it locally. But the composition of the simple functions may be complex. So instead of doing it at one step, so you kind of use the structure of the network and redistribute these values layer by layer. So this is the whole idea. So you kind of get this advantage. It's very fast, and you get very good explanations because you simplify the problem. But there's a price to pay is that you need to know the structure. You need to know the inner details of the network. For example, in this perturbation-based approaches, you don't know anything. You don't need to know anything about the model. So you just observe its reaction to the changed input. Here, you need to know all the details. But in many cases, we know we have access to the internals. So why not using it to simplify the explanation process? And the first kind of rule which we came up with to redistribute relevance was, we thought maybe we should take two factors into account. One factor is the strength of the activation. So it means the more activated a neuron becomes in the forward pass, the more important it is for this particular image, because it encodes certain shapes which are present in the image, which are related to the rooster. So this XI here tells you that the higher the activation, the more relevance it should get. This is the one factor, and the other factor is this Wij, which is the connection between these two neurons, between these two layers. So the more connected they are, the more relevance should flow along these lines. So kind of the idea is to proportionally redistribute relevance from the layer above to the layer below. And we came up with several rules. They have some theoretical interpretation. I will talk about it in a second. But in the end, if you do this propagation process, you get relevance values for every layer, for every neuron, and also for the input. And for the input, you can visualize as a heat map. In this case, you see the rooster's head.
Can I disturb you?
Yeah.
Yeah, I just had a question about this. So when you are doing this, finding out what activated weights, is it for every iteration you are doing, or it's after training the network?
It's after training the network. So you,
okay.
I mean, you could. I wish later I will show you an example where we do it during training. But in most cases, you want to explain the model after training.
Ah, okay. Yeah. Okay, thanks. That's it.
So I will show you a lot of different applications where we kind of look at these different things. But you have a very rich information, because you know the relevance for every neuron, for every weight, and you can visualize it. Yeah,
that's true. That's important.
And now I will show you a bit of the kind of theory behind it. I will just very briefly talk about it. We can discuss it later if you are interested. Because I mean, this is the idea of decomposition which we have, right? So I told you that I have our function value, which I want to decompose in relevance scores, and every dimension should get a relevance score. So you want to have a sum over the dimensions equals your function value. This is what you want to achieve. And like the standard tool for doing such a decomposition in mathematics is Taylor expansion. So if you have a function, you can expand it. And if you find a nice root point, x tilde here, then this first term, f of x tilde, becomes 0. And what you have is the sum over your dimensions plus some higher order term. But for many simple neural network models, this higher order term doesn't matter. But the idea is that you have right away, you have this decomposition by using Taylor expansion. Here you expand your function from input to output. The whole function you kind of approximate. This is a valid approach. It works well for simple models, but unfortunately for neural networks, for deep neural networks, it has some big limitations. The first thing is that I told you this gradient shattering problem, that for neural networks, gradients become very much noisy and not really reliable with depth. There is some theoretical work on that, where people showed that gradients have like this problem. This is one thing. And the other problem is that it is difficult to find a good root point in this approach, because you want, if you approximate your function, you want the root point, this x tilde, to be very close to x, but it should have the property that f of x tilde is 0. So ideally, it should also lie on the manifold of your data distribution. So if you have, for example, images, this should be an image. So in this case, ideally, your x tilde would be an image with the same background, but without the rooster. But it's very hard to construct such an image, because if you would know that the rooster should be removed, then you would know what is relevant in the image, and you wouldn't need to explain the function anymore. So finding a good root point is difficult. You can always use, for example, a root point at 0 at the origin for many networks, but this root point is very far away from your actual input. And therefore the decomposition will not be really meaningful. But there is a trick which we kind of showed, that instead of decomposing the whole thing at once, you could also use the Taylor expansion idea, but decompose things layer-wise. So in other words, assume you have already redistributed your relevance until layer k. So you have the values rk, and you know that this relevance value only depends on the activations in the lower layer, because everything is deterministic. Once you have these activations, you have the prediction, and once you have the prediction, you have the relevance values. So you can represent the relevance at layer k as a function of the activations of A. And you could apply the Taylor decomposition trick to this function. And this will tell you how to optimally redistribute relevance to the next lower layer. So here we kind of came up with an intuitive rule. So we just thought about a good rule, how to do it, and just came up with it. Here we are using a tool from mathematics, Taylor expansion. We represent the relevance as a function and use Taylor to guide us how to redistribute relevance. And the key advantage is that one can show that explaining this relevance function is very easy, which means it's very easy to find a root point, and it's and you don't have the gradient shattering problem, which you have here, because you are not explaining everything in one shot, but you are explaining a much simpler function. So you can prove that this relevance function is just like a scaled ReLU, just a scaled ReLU. Therefore, it's very easy to analyze. So it's very easy to find a root point for this function. And this is what we did. And it's what we got as a result is that if you do it like according to the Taylor decomposition framework, if you do it kind of optimally in the mathematical sense, you will arrive at exactly these rules which we initially handcrafted. So this is something which we were very happy at, because at first we handcrafted the rules and then had a mathematical theoretical foundation for them. Okay, so we can talk about the details later if you are interested. I will just like repeat the intuition of LRP is that to robustly explain a model, we kind of leverage its structure. So we know that the network is a composition of neurons, and we exploit these facts in the explanation. So instead of explaining the whole thing at once, which is hard, we kind of explain things layer-wise, layer by layer, and which is easy, because we can show that the relevance the relevance function is just the scaled ReLU. And what we also like from this analysis, what we understood is that it makes sense to use different redistribution rules for different layers, because every layer has its own property. Like, for example, the input layer or the convolution layer or the fully connected layer, they are different. They have a different property. They have a different support. For example, if you have a ReLU activation, you get the outputs only are positive or zero. If you have an input layer which consists of pixels, you often have a box constraint. For example, the pixel values are between 0 and 255. If you have as input word embeddings, you don't have this constraint. So every kind of type of layer has different support, different properties, and it makes sense to adapt the choice of root point to these properties. And if you do it, you will arrive at different redistribution rules. And for different layer types, it makes sense to use a different rule. And we also have some recent work describing this property. So this was kind of the technical part. Are there any questions to this technical part?
Yes, if somebody has question, can ask now. They can raise hand or put some questions in chat. I think it's good to us if you have not followed something before going ahead. Maybe no.
I mean, we will also have a chance to ask later. So if you
yeah,
if you want, you
so
can.
I have one question before we go, maybe. So what determines the error of this for LPR when you do this? What parameter? What is the error? How you estimate that?
Which one?
Error in doing layer-wise propagation. So how do you estimate that? There may be error, right?
How do you,
not be accurate.
How do you estimate the error?
Yeah.
I mean, you in some sense you don't have an error, because you are kind of redistributing the value according. You're not fitting anything. You're redistributing the value according to the assumptions you make about the root point, for example.
Right.
And
okay, so
this gives you like a propagation rule, and in the end you will have a redistribution which is conservative. So you redistribute. I mean, maybe what you are referring to is how can you know how can you evaluate the quality of an explanation? This is something this is something there is still an ongoing discussion on that, but there is many works targeting that. So I have here summarized some of the recent ones. So how can we know what is a good explanation?
Yeah.
And there are different answers to it. So one answer is that you can introduce some axioms. You can, for example, have some axiomatic approach and say, define some properties which you think an explanation or an explanation method should fulfill. For example, you can think that explanations should be smooth, or like for two inputs which are almost identical, you may require the explanations to also be almost identical. Some kind of smoothness property. You could define it as a desired property. And then you can see maybe that some of these methods which I showed fulfill these properties, others don't. There are other properties which you can kind of define. Or what you also could do is, once you have this explanation, you can evaluate the quality or the faithfulness of this explanation by something called pixel flipping. Or so you could try to distort or put some random noise on the pixels which are relevant, and then see how the model reacts to it. If the explanation was good, then it should destroy the model's prediction. If the explanation is random, then the model prediction should not be much affected. So there are different ways to kind of quantize this quality. Another one is to use ground truth information. There you can compute the error, but this you can only do, or at least we have some recent work on that, but we did it on some simulated data, some target data, because you need to have access to the ground truth. You can design your experiment in a way where you know what is relevant, and then you can see if your model is also like giving this answer to you. And there are also like a couple of other approaches, but there is still no theory of explanation. So therefore it's hard to quantify the quality, but the field is moving slowly into this direction. And also some people say that explanations are good if they're useful, if a human or someone can do something with it. So it's more like a utilitarian view.
Okay, slight subjective now. Okay, thank you.
So, I mean, this LRP has been applied to all kinds of data. I mean, this is just like our work, or like at least a subset of it. So we applied it to images, to videos, to computer games, to medical data, to text, to speech. And then I know from other people, also like people in climate science or meteorology, or people in astronomy also use this method to explain their models. So there are various applications today. And it's a very generic technique, and it can also be applied to different models, different problems. So not only like to deep neural networks. So let me give you some example which you may which may be interesting to you. So there was a big international challenge on image classification. It was from 2005 to 2012. The task was to classify 20 different categories. So images in 20 different categories. These images were real life images. So they were sometimes not very easy to classify. And kind of the best teams in the world, the best universities participated in this challenge. And every year they submitted their results on a test set, and this was evaluated, and there was a ranking list, and it was very prestigious challenge in this area. But at that time, nobody knew what the model is really learning. So what they only reported were average classification rates or mean AP scores or something like that. Nobody had a clue what the model is really doing. And what we did is we took the winning methods at the time and applied it to these images and computed explanations. And you see that the model is really doing strange things. So the winning method is not doing what it is supposed to do. It classifies ships by the presence of water. It classifies trains by the presence of tracks, and it classifies horse images by the presence of a strange copyright watermark. And we didn't understand it, and just we're like really puzzled and had to look at the data set, at the horse class. And it turns out that a lot of horses in the data set have a copyright tag, because these images were kind of crawled from the internet, from some websites with horses, and a lot of websites with horses have a copyright tag, apparently. And nobody realized it for almost a decade. So like hundreds of people were participating in this, and nobody had a clue. And because nobody can analyze all these data, it were like thousands of images, and nobody realizes this bias and this bug in the data. And we referred to this phenomenon as a clever Hans predictor. So maybe if you are not familiar with it, I recommend to Google or Wikipedia to check what is clever Hans. Kluger Hans was a German horse which was supposed to do math. People believed this horse can do math, but apparently it couldn't. And I recommend to read the Wikipedia article on that. So it's a really fun story. And we see a lot of clever Hans predictors also like in nowadays. So this was just one example from the old times, but if you look at the more recent ones, for example, we trained a face classifier, a deep neural network to classify an age and the gender of the person, or age and sex of the person. And so age was kind of classified in different age ranges. And apparently this classifier also had a clever Hans property, at least the one. So we trained two. The one, we used a pre-trained neural network, pre-trained on ImageNet, which is a generic image database. And we also pre-trained one classifier on EMDB Wiki, which is a large data set of faces. And the ImageNet classifier had the problem, for example, for this lady. This lady was classified correctly as belonging to the category 60 plus, so 60 years and older. But you see that the mouth region, so this lady is laughing, and the mouth region, the fact that she is laughing spoke against this classification. So the blue part means that something contradicts the prediction. So there are many features which speak which supports this prediction, like the hair and the eyes, which support the network thinking that this lady belongs to this category or to this age class, but the fact that she is laughing speaks against it. In other words, that the network has learned that old people do not laugh. And the same you can see with the guy on the right. He is also like laughing, and you immediately see that the model is reacting to it and is saying, it is assigning negative relevance to it. So in this case, it seems that the model is really learning that all people don't laugh. So it's a clear bias in the data. If you pre-train your model on this face data set, you don't get this bias anymore. Something which is which you see in the lower row. So even today's models are biased and have a clever Hans tendency. So you should better be careful when using models for your applications. You better explain them. So you see also the accuracy. If you pre-train on this face database, it also goes up. So this were like two examples which you can count as verification. So we verified that the model is doing what it's supposed to do. In this case, it didn't do what it was supposed to do. But you can even go beyond this visualization. This is what I meant before, that we trained a classic like an agent playing Atari. So the task was to play this game of Breakout, and on the left you see the red color indicates the relevant areas, and you see that on the left corner it's actually relevant all the time, and you will see why. So the model like learned a very clever strategy to play this game, to build this tunnel and play the ball and make a lot of points without risking to lose the ball. A very clever strategy. And you see that you could observe this, you could observe the intention of the model beforehand. And what we did is we analyzed this model. So we analyzed the learning behavior over time. So on the x-axis, you see the training epochs. And we see that the first thing the model has learned, the green line, is that the ball is a relevant element of the game. Then after some epochs, the model learns that the pedals, the thing which you need to hit the ball, is a relevant one. And only after 50 epochs, it learns to build this tunnel. So you can study the dynamics of learning with these tools. And we could also compare the learning behaviors of different architectures. So here you see the same curves for different architectures. So this was another application of these heat maps, of these explanations. And you can even go beyond. You can try to aggregate these explanations. So assume you have a data set. You could explain every sample and then try to cluster the explanation, try to identify some structure in the heat maps. And you see in this example that there are like some prototypical strategies of the model to classify the horses. So there is this copyright tag strategy, but there is also like another one where the model is looking at some features in the image, like these things, the horses jumping above. And you can kind of do the clustering using, for example, spectral clustering. This is what we did here. So as you compute some affinity structure on the heat maps, you can compute some eigenvalue spectrum and perform clustering. And if you have, like in this clustering, if you have a large eigenvalue gap, you know that there are, like how many classes, how many different clusters you have. And you see, for example, here that this is a class of airplanes, and you see two distinct clusters and two distinct strategies of the model to identify airplanes. In the blue cluster, the model is really looking at the airplane. In the other cluster, it assigns a lot of relevance to the upper and lower part of the image. And we later found out that this artifact was due to some padding, which we did on the images, because these images were input to a neural network which only accepted square images. So if the images were not square, we had to pad them, and this padding artifact was picked up by the neural network. So you see, if you put some random noise to the borders, the prediction goes down, although there is still an airplane in the image. So it's like very unstable behavior. And recently we are moving one step forward. We are trying to automatically detect this clever Hans problem. So we apply this. We apply some spectral analysis and try to find out if there are some outlier clusters, because outlier clusters tell us that there is something strange, some strategy which is not usual, which is unusual. So for example, here, this is like on ImageNet, which is like this very large data set, which also has certain problems, which I think many people are not aware of. So even like this carefully collected data set has also some copyright tags in the truck class. It has some other things which are bad which affect the classifier. And what we tried is we tried to remove this effect. We tried to unlearn. In this case, we tried to unlearn the copyright tag bias. So we, on purpose, modified, like did some fine tuning on the model and tried to unlearn this bias. And you see that in some cases we were successful with that. So this work is very recent, and it goes into the direction of improving your models with XAI. So if you see that we are far beyond just looking at the explanation. So we are not only like having these explanations and saying, oh, it's a cool heat map, but we are using it for something, for improving the classifier. And we have some other recent work where we directly integrate these explanations into training. So this is a very specific task, is cross-domain few-shot classification. And so you have some query image, for example, image of a dog, and then you have some example images of support. And what we tried out is to integrate, use the heat map as a filtering tool, and not only like use the features on the original image for the classification, but also like use the features on the filtered image to better get an idea on the object of interest. And combining these two losses brings an advantage. It's not much, but it's significant. But this is like one of the first works in this direction. So I think there's a lot of potential to improve your models using explanations, or make them more trustworthy, avoid that they become clever Hans predictors. Another work which I think is also very relevant is to transfer these concepts of explanations to non-neural models. So we were thinking, okay, how can we explain, for example, clustering solutions? And what we came up with is an idea which we call neuralization, the neuralization trick. So the trick goes as follows. So if you can't explain your algorithm, for example, your support vector machine or your clustering solution, try to neuralize it, try to convert it into a neural network because we know how to explain neural networks. We have all the tools, we have all the machinery, we have all the theory for explaining neural networks. So if you convert your classical algorithm into a neural network, then you can also explain it. And this is what we did with clustering. So I will not go into details here, but also here that the idea is that we have a clustering solution. So we trained K-means or soft K-means to give us a clustering. And then from this clustering, we converted the cluster membership probability into a neural network. So we use the neural network to estimate the cluster membership probability. So you can do it not only for standard K-means, but also for kernel K-means or deep K-means. And with that, we can make clustering explainable. So here we clustered VGG internal features, and you see that you see a nice clustering. You see that some of the shapes encode certain like complex objects, whereas others are more textures or buildings or parts of the buildings. So you can cluster these things and get and not only like and also like explain and visualize what is the property of what's the relevant part of an sample belonging to the cluster. So you know what makes this sample relevant, why the sample has been assigned to this cluster, which features were relevant for that. Another work, I would just like very briefly mention it, use explanations for pruning, because you saw here with LRP, we know we don't only have the heat map at the input level, but we have the relevance values for every neuron and for every connection, for every weight. So this is something which you can use for pruning. So you can, for example, remove every connection or every neuron which is not relevant or whose relevance is below a certain threshold. And this is what we did. So we first computed predictions and the relevance, and then remove neurons iteratively which were not relevant. And you see if you do it like if you LRP is the red line, the pruning rate you can increase very much without affecting the accuracy of your model. So in this case, we only have like only 10 samples per class, and it was a domain adaptation scenario. So we had like a large neural network trained for 1,000 classes, and we wanted to prune it for a subset of classes using very little data. And if you just use some other criteria like the weight magnitude or the gradient magnitude, you get a drop in test accuracy. But if you use relevance values, the test accuracies stay high for a long time. And finally, we also applied these methods in the sciences. So I will give you just an example on some medical data. Here we trained a model for decoding fMRI signals. So the task is like a big data set, publicly available. People were put into a scanner and were shown some things, and we needed to decode them. Or there was some certain like protocols, like an MBAC task, but the important information is that there are 4 different types of classes, like faces, places, tools, and so on. And it was a decoding task. So you need to decode this information from the fMRI signal. And the fMRI signal is like a high dimensional data. So you have a 3D brain volume, and you have also like measurements on different time points, and we trained an LSTM CNN model for that and applied LRP for it. And the cool thing is that you get these explanations not only for every subject and every block of trials, but also for every single trial, for every single volume. This is something which is much better in this sense than this classical analysis, because in classical analysis, people just compare groups of subjects and have these p-values on a subject level or the group level. And here we get relevance values for every trial and every volume. So we can also study the dynamics of the processing going on in your brain. This is something which we currently are looking at, and which gives us whole new opportunities to study this complex data. We also applied it to some histopathology data, and you can see here some example. And also wanted to know if we can detect this kind of clever Hans artifact with that and some biases. So we defined we did several experiments where we added some bias, for example, some data set bias, some label affecting the entire data set, or some class correlated bias, some artifact which is corrupted only with one class label and so on, or some sample bias. So we kind of looked at these different scenarios and showed that in many of these cases, you can detect the biases from a single input, from a single image. So if you are a pathologist, you would immediately see that something is going wrong, something is wrong. So in this case, the explanation is a nice tool for verification, because it tells you, it allows you to verify the reasoning of the system, and if there is a bias, if there is something strange, you can immediately detect it. And here is an example. So the cool thing is also that LRP gives you pixel-wise explanations, and not like methods like RedCam or some probability maps, which are very low resolution. Okay, so let me conclude. So we saw that there are many methods available. We saw that LRP and propagation-based methods are quite good in terms that they are efficient, and they are grounded in there is some theoretical grounding or foundation of them, and you get nice results. The price to pay is that you have to know the details of your model. So you have to know the internals, which is in many applications, it's totally fine. We saw some examples where we applied it for visualizing the predictions, explaining the predictions, but we saw a lot of examples where we go beyond. And this is something I'm currently working on, and I also organized an ICML workshop last year on how to move beyond simple explanations, how to use them for other tasks, for pruning, for improving the model, and so on. And also for some interesting scientific analysis. So there is also some reading. Recently, our paper was published in Proceedings of IEEE. It gives you a nice overview over all these methods and applications, and it's very highly recommended also for beginners wanting to dive into the field. We have a lot of papers on different topics, tutorials, methods papers on the beyond question, on evaluation, on this dataset bias, software, application, text, images, video, and so on. I've edited the book 2 years ago. I'm currently editing a follow-up. So here you can find the current state of the art. It's not only about the explanation methods which we're talking about here, but also beyond that, on methods for interpreting AI systems. And we have web page where you can find tutorials, also some software, online demos, and slides, so you can check it out and also have a read through the papers. And with that, I'm very happy to take questions.
Thank you, Wojciech, for giving a nice perspective, very different. How relevance is important you have shown in this tutorial. So I think it's open for questions and discussion. So if anybody has question, can raise hand or put in the chat so we can take them. Okay. Let's see. Okay. So anyway, I think meantime I may ask. Okay, somebody has raised hand. Rafael. Okay, you can unmute and
I start typing, but I'll be more than happy to ask the question out loud. So Dr. Samek, I have a question from the perspective of your experience with working with imbalanced data. Did you try to maybe visualize the data which has the significantly imbalanced classes, like 1 to 50, 1 to 60, or even ratio that high? Do you notice that the networks are behaving differently, that this idea of clever hands being maybe more common in the rare classes versus the frequent? Did you work on any cases like this? Lots of those benchmarks that you're using, right? Those are quite balanced data sets. So I'm kind of curious.
Yeah, that's a very good question. I think that's certainly true that if you have an unbalanced setting, you are at a greater risk of running into these problems. But you also have to know that in the end, it's also like the way how you design the task, how you train your network. There are also like different losses proposed in the community to train your networks which are more robust to unbalanced classes. So if you just do it like very naively and just, for example, maximize the average loss, then of course you will neglect maybe the classes which are very which are not representative. But there is some work which kind of tries to get rid of this problem and tries to get solutions which are more fair. And if you would explain maybe these networks which are more fair, then you will get better results. But this is certainly something which is worth being studied. I haven't looked at this systematically.
I have another question, and that's the last one, I promise. So you show some work with neuroscientists and on the histopathology data. Lots of this seems like AI is at the phase of trying to explain how the model works. What about discovery of new knowledge? Did any of those medical experts were inspired by any new discoveries, or for that, hey, maybe you're discovering something that they didn't think of?
I think this is a big hope and the big promise that you apply your network to your complex data, and then the network is learning something which you were not aware of. For example, having a connection between the genes, some genetic profile, and the disease or something, and then once you explain, you get a new hypothesis, which then you would need to test in an independent experiment or in further studies. But this is something I think many scientists are very much hoping that they can use these tools to get some new insights, new hypotheses.
Did you experience something like this or not yet? What do you think? Yeah, that's exactly.
I mean, not something which is kind of groundbreaking. I think the things which we found were mostly like consistent with what is known, right? So in the end, you're also happy if your network has found something which goes in line with what is known. But of course, it would be much cooler to find something which is maybe different and which
inspires
gives you a hint, inspires you to some new analysis, but I think this is something which is quite difficult, right? So it's
yeah, definitely. I was just kind of curious. Thank you so much. That was a great talk. Thank you.
thank you. And I think what is also like interesting is also because I showed you a lot of image examples, but what I'm also currently interested in is how to get explanations and how to make sense of explanations for data which is maybe not explainable, or for sensor readings, for time series data, which is much harder for human to interpret the images. For images, we immediately know what's going on, at least for real world images. But if you have some data which is some time series, which is some features which you don't understand, so it's very hard also to make sense of it.
And there's some data in time series that, I don't know if you're familiar with Keogh's work on the shapelets data, when they basically claim that they could discover shapes of fish or any data that translate to the sequence. That could be kind of, a way of visualizing and kind of seeing, hey, could I verify this with the neural networks? Is this discovering the same shapelets? Yeah, that would be really exciting.
Yeah. I think, yeah, I think, I mean, there is also this line of work where people try to, yeah, kind of see if like this some kind of shapelets, also shearlets or whatever.
Yeah, whatever they call it. Yeah,
is also learned by networks. Yeah,
you're right. This is just not as intuitive as the images are for us. Definitely. Thank you.
Anybody else? Okay. Maybe. So, how does this changes with network architecture? Like, everybody is using different architecture, right, for training and learning. So, does it change like the complexity we face if you change the architecture?
Yeah, I mean the explanation can change. So in the end, the explanation is giving you the model's view on how it solves the problem. So if you have different architectures, or maybe if you have two models, they may solve the task in a different way, and this may lead to different explanations. We haven't like systematically evaluated things. I mean, we saw that certain architectures, for example, have explanations which are more sparse than others, but sometimes it's hard to compare them because they maybe have different number of layers, so it's different types of layers. So it's certainly something which is worth being studied systematically. Unfortunately we didn't do that so far.
Okay. And what is what you can suggest for beginners? Suppose somebody wants to use this technique. So where to start mainly? From this your website, or you suggest something?
Yeah, I think, I mean, a nice overview paper is this Proceedings of IEEE 1.
Okay.
And this is like the paper which you can read, and there is also like some work through examples and some also like something about implementation. But we also have some toolboxes. So on the web page you can find some links to some toolboxes which you can use. So if you use some TensorFlow or like PyTorch or some other frameworks, you can use these toolboxes.
Okay, great. Okay, I think that's it. We have anything. Okay. Oh, we had enough time, but okay, we have still more time left, but depending on maybe. Okay, so I don't think any questions are there. So maybe we can conclude, or do you have anything to show? You can show, it's up to you, because we still have a time.
No, I think in terms of
Yeah.
slides, this
Done.
was it.
Okay.
Yeah, I mean, if some questions come up, you can always also like email me or contact me also later.
Okay. Okay. So fine. Okay, there is a comment from Alessandro. Great talk. Very exciting to see that you were able to remove the copyright bias. Okay. Good. Okay then. Thank you for giving this wonderful talk and educating us about this new stuff, which we need really. We need to interpret not only, we don't want to have a neural network as a black box, we want to interpret it. That is most important. And I think this will add into that knowledge. And this could be useful even heliophysics or other science disciplines, solar physics and any magnetosphere or climate. Even I think it should be able to extend this technique. One just need to think what problem you want to tackle and how. So thank you for educating us for that, and thank you everybody for joining us. So tomorrow, please join us at 8 a.m. 8 a.m. Mountain Time for plenary sessions, and tomorrow also we have parallel sessions. So see you there. Thank you everybody. Bye bye.
Bye bye.
Yeah. Okay. So Sharon, that's it, right?
Yes, that's very good. I just was making sure that no more questions came in. I think we had between 15 and 18, so for most of the time. So it stayed really steady. It was great.
Yeah, and it was more than what we expected. So, okay.
Okay. Well, I think we're good. I guess we'll see you tomorrow morning then, right?
Yeah, sure. I think Lika is also there, right?
Yes, she is. Unless I wonder if she's on multiple meetings. So
multiple stuff, maybe. Okay.
Okay.
See you tomorrow. Thank you very much.
Thank you. Bye-bye, Ankush.
Yeah.